Okay, so now we're going to talk about the operation of multiplication. And as we have been doing with our other operations, we begin with a definition. We simply define multiplication of whole numbers as repeated addition. So what that means is that, for example, the multiplication problem 3 times 5 can be interpreted as 5 added to itself 3 times. It's worth noting here that this definition is actually incomplete, as it will not make sense when we talk about multiplication of fractions or decimals. At those times, we will need to come up with new interpretations of multiplication. But this certainly makes sense with whole numbers. Models of multiplication, how can we associate this repeated addition definition with previous models of how numbers are used? We have a set model, which interprets 3 times 5 as simply 3 groups of 5 objects. A measurement model, we can interpret 3 times 5 as 3 jumps of 5 on a number line. And kind of a slight abstraction of a number line is a bar diagram. And again, we are using bar diagrams in the context of solving word problems. So we're going to want to be able to associate a diagram like this with the operation of 3 times 5 as well. Okay. Now, these are models that we have seen previously, but with multiplication, there's actually a new model that comes up, which we call a rectangular array model. And a rectangular array model, we can interpret 3 times 5 as simply 3 rows of 5 objects. The objects can be anything. You're going to find out pretty quickly that the easiest objects to draw are indeed squares. So we might have a rectangular array that looks like this to interpret 3 times 5. Now, it should be mentioned that even though this looks like something we might use to talk about area of a rectangle, we don't want to make an area association at this point because students don't know anything about area of rectangles at this point. In fact, we're going to actually do this in the other direction. Since students will hopefully be introduced to the rectangular array model from an early age, when it comes time to learn the area of a rectangle, hopefully they will be able to associate the area of a rectangle with a rectangular array model, and then the familiar formula of length times width will make perfect sense to them at that time. Okay, so since, as we've seen, multiplication is in fact defined in terms of addition, it stands to reason that many of the properties, the arithmetic properties that hold for addition, namely the commutative property, the associative property, and the identity property, also hold for multiplication. And they do. So multiplication certainly does satisfy a commutative property. For example, 3 times 5 is equal to 5 times 3. Remember, the commutative property is essentially the one that says it does not matter in which order you operate on numbers if the operation is addition or, as we see now, multiplication. As we discussed with addition, we don't just want to tell students these properties. We want students to either figure out the properties on their own, or we want to justify to the students why the properties are correct. This is not terribly difficult to do in the case of multiplication, and the rectangular array model can help us out. If we just look at this array for 3 times 5, if we look at this straight on, then we clearly see 3 rows of 5 objects, which we interpret as 3 times 5. However, if we tilt our head, now we see 5 rows of 3 objects, which we would interpret as 5 times 3. And since I didn't do anything to the diagram, I didn't do anything to the model, the same number of squares are certainly there if I look at it straight on and see 3 times 5, or if I tilt my head and I see 5 times 3, that must mean that 3 times 5 and 5 times 3 are equivalent. Multiplication also satisfies an associative property. And to illustrate the associative property, I'm going to draw a very crude picture, so I apologize in advance for the crudeness of this picture. But again, recall that the associative property tells us how to deal with addition or multiplication, in this case, of more than 2 numbers at a time. So for example, if we wanted to multiply the numbers 2 times 3 times 4, we have to choose which ones we want to multiply together first. The associative property tells us it does not matter what choice you make. So for example, if we wanted to multiply the 2 times 3 together first, we would denote that by putting parentheses around the 2 times 3. Then we, in this case, would get 6 times 4 because we've been multiplying the 2 times 3 together first. The associative property tells us we're going to get the same answer that we would get if we were to choose to multiply the 3 times 4 together first. Okay? Now, the crude picture I was referring to is imagine 2 shelves of flowers. And on each shelf, there are 3 boxes of flowers. And each box, it's going to look like strands of grass, but on each box, there are 4 flowers in each box. So 2 shelves, on each shelf 3 boxes, in each box 4 flowers. Now, what we are going to do to illustrate the associative property is to illustrate that the left-hand side and the right-hand side of this equation are identical. And we're going to do that by simply counting flowers. Okay? Now, on the one hand, if we were to count flowers using the arithmetic on the left-hand side, we are counting 2 times 3 first. Now, 2 times 3 corresponds to the total number of boxes that we see, right? Because there are 2 shelves, and on each shelf there are 3 boxes. So 2 times 3 represents the total number of boxes. And then if we were to multiply that number by 4, we would get the total number of flowers, right? Because there are 2 times 3 or 6 total boxes. In each box there are 4 flowers. 6 times 4 gives us our 24 total flowers. So if we count flowers in that way, meaning boxes first and then flowers, we get the arithmetic on the left-hand side. But that's not the only way to count the flowers, right? There's another way to count the flowers, namely by using the arithmetic on the right-hand side. What the right-hand side does is it multiplies 3 times 4 first. So 3 times 4 refers to the number of flowers on each shelf, right? Because on each shelf there are 3 boxes, and in each box there are 4 flowers. So 3 times 4 represents the total number of flowers on each shelf. Then when we multiply by 2, we get the total number of flowers in the diagram, right? Because if there are 12 flowers on each shelf and there are 2 shelves, then 12 times 2 represents the total number of flowers. So the associative property can be illustrated simply by illustrating a picture like this, counting the flowers in 2 different ways. Okay. We also have, as we did with addition, we have an identity property. And remember that in mathematics, an identity of an operation is simply, in this case, a number. And since our operation is multiplication, it's a number that does not change a given number under multiplication. And of course, that number is 1. So for example, we would say that 1 times 5 is equal to 5. This certainly is something that needs to be explained to students, but once it's explained, it's very easy to catch on to. Any number of our interpretations can be used to validate this point. For example, we could use repeated addition. We are adding 5 to itself once. Of course, we're going to get 5. If we have one group of 5 objects, we're certainly going to have 5 objects, et cetera, et cetera. So this is a pretty easy property to get a handle on, but of course it does need to be explained. So far, we have connected all of the properties that held for addition to multiplication. It does turn out, however, that there is a new property that we haven't discussed yet that actually connects multiplication with addition. And it is probably not an exaggeration to say it's the most important arithmetic property in elementary school. And this is the distributive property. Oops. As we'll see in later clips, the distributive property is the main arithmetic property behind the multiplication algorithm. It's also behind several mental math techniques and is used a lot in algebra in high school when we do things like factoring. So the distributive property is a very, very important property, and it's not at all obvious when you look at it on the surface. What the distributive property tells us, an example I should say of the distributive property is the following. That, for example, if we multiply 2 by the quantity 3 plus 5, that's the term we use when we have a sum in parentheses. This is equivalent to multiplying 2 by 3 and adding that to the product of 2 and 5. Okay? And again, this is not something that is maybe as intuitive in terms of properties as the other properties are, but it's nevertheless true and very, very important. This property, again, can be illustrated with a picture, and again, we're going to use sort of a rectangular array here. And as we've done with our previous pictures, we've drawn pictures, and we have just kind of looked at the pictures in 2 different ways to represent both sides of an equation. Okay. So the left-hand side of the equation is essentially 2 times 8, right? Because the 3 plus 5 is equivalent to 8. So 2 times 8 can be represented by a rectangular array as 2 rows of 8 objects. So that's what I'm going to start drawing, is just 2 rows of 8 objects. And of course I'm going to use squares, 1, 2, 3, 4, 5, 6, 7, 8. So if we look at this diagram on the surface, it represents the left-hand side of the equation, right? I'm just choosing to write the number 8 as 3 plus 5. Right. Now, going to take my pen and do a little creative shading to this diagram. Notice, I did not add squares to the diagram, I did not subtract squares from the diagram, so the total number of squares in this diagram is certainly equal to the total number of squares in the original diagram, which we saw was 2 times the quantity 3 plus 5. But now, we can see that if we add the shaded to the unshaded portion, we see the exact right-hand side of the equation, right? The shaded portion is 2 rows of 3 boxes, which under the rectangular array model is 2 times 3. The unshaded part, however, is 2 rows of 5 boxes, which again, according to the rectangular array model, is 2 times 5. So if we use the idea that a whole is equal to the sum of its parts, the shaded parts plus the unshaded parts are equal to the entire diagram. So we have another instance where we draw a diagram, we look at it in one way to represent one side of an equation, and we just look at it in a slightly different way to represent the other side of the equation. Since the diagram hasn't been changed, the 2 sides of the equation must be equal. Okay. One thing I want to mention about the distributive property is that in many cases, the distributive property is given in textbooks in a form similar to this. Through talking with teachers, I've noticed that oftentimes students just, when they learn a property, they lock into exactly what the property looks like in the book or exactly what the property looks like when it was demonstrated to them in class. What I mean by that is when they connect something with the distributive property, they're only going to be connecting things that look like this left-hand side. A number multiplied by a sum in parentheses. Okay? Now, it might be worth your while as a teacher to also mention that there are other kind of different looking forms of the distributive property that students need to make a connection to as well. So, for example, other forms of the distributive property, well, if I just interchange this sum with this factor, as I can do through the commutative property multiplication, I get something that looks like this. Now, for those of us that are comfortable with the distributive property, we still notice that this is an example of distributive property, but a student who's just locking into how a specific form looks might not make that connection. So it's probably worth mentioning when you introduce the distributive property that even if something looks like this, the distributive property can still be used. If you have a quantity multiplied by a number, then this is still governed by the distributive property. This is still going to be 3 times 2 plus 5 times 2. It's also worth mentioning that the distributive property works if our operation here is subtraction as opposed to addition. So for example, and this is going to come up when we discuss mental math strategies here in a bit, if you have a problem like, for example, 6 times the quantity 10 minus 1, the distributive property still holds here. This is equivalent to 6 times 10, in this case, minus 6 times 1. So even though it's kind of hard for us as teachers to see the need for mentioning this because we're so comfortable maybe with the distributive property that we just kind of automatically know that if this makes sense, then these should as well. Students don't automatically make that connection, so it again might be worth your while to take a few minutes when you're discussing the distributive property to discuss these kind of alternate looking forms as well. Okay. Now, as we've been doing with our operations, we have mentioned that we kind of have 2 main goals in mind when we discuss our operations. On the one hand, our students need to understand the concepts, the definition, the models, the interpretations of each individual operation, so they will be able to solve real-world problems. So they will be able to connect a real-world problem to the correct operation. But they also need to be able to compute, right? And when we talk about computation at an early level with multiplication, really what we're talking about are multiplication facts or times tables. I don't know if they still call them times tables, but that's what I called them back when I was in elementary school. And the mastery of multiplication facts is one of the most important benchmarks there is in early elementary school. Yet it's also very common for students to lag behind in learning their facts. And if you lag behind in learning your facts, if you do not know your facts by 3rd grade, then you're going to kind of be behind the 8 ball for mathematics that is to come later on. Again, we discussed a table like this with our addition facts. Again, not sure if they still do it this way, but when I was in elementary school a long time ago, I was given a sheet of paper, the numbers 0 through 10 along the top, the numbers 0 through 10 down the side, all of the answers to the multiplication problems in the middle, and was taught just to learn. Okay. As we discussed with addition, there are 121 total facts to learn. There are 11 numbers across the top, there are 11 numbers down the side. Okay? And as we discussed with addition, we do not want to rely solely on memorization for learning these facts. In fact, if we can use the aforementioned properties, commutative property, identitive property, and other properties to our advantage, we can come up with thinking strategies that can greatly reduce the number of facts that actually need to be memorized. Okay? I will attach a PowerPoint to this, this clip that will go into that in a little bit more detail, but I do want to take a little bit of time just to show you how very quickly we can take 121 facts and reduce it to a very, very manageable number using some very basic properties. Okay? So, for example, I've got to memorize these numbers eventually. If we just use the commutative property, we can reduce the 121 original facts down to 66. So again, the commutative property is just saying, if you know what 3 times 6 is, for example, you automatically know what 6 times 3 is, so you don't need to memorize both of those multiplication facts. You don't need to think of those as 2 separate facts. You can think of those as just one fact. Right? So automatically we're down from 120, or right off the bat, I should say, we're down from 121 facts to 66. 66 still seems like a lot. But we can also use other thinking strategies to our benefit as well. Multiplication by 0 should not require any memorization. I mean, we didn't discuss it as one of our properties, but multiplication by 0 can be taught very, very quickly. If you have, what's 0 times 4? If you have 0 groups of 4 objects, you don't have any objects, right? So it shouldn't be too difficult to explain to students that any multiplication by 0 returns 0. So any column or row in this, in your multiplication facts that involves 0 should be an automatic answer. Also, any column or row that involves the number 1 should be an automatic answer because of the multiplicative identity property. Multiplication by 1 returns the number you're multiplying by. 6 times 1 is equal to 6. 9 times 1 is equal to 9. Those facts should not require any memorization. Multiplying by 2 shouldn't require any memorization because we should already know all of our multiples of 2. Multiples of 2 correspond exactly to our doubles facts from addition. 6 plus 6, for example, is the same as 6 times 2. Since we should know all of our doubles from addition, we should know all of our multiples of 2. Multiples of 5. There are mental math techniques to help us with multiples of 5. But again, skip counting is something that is a useful tool for multiplying by 5. Just count by 5s. 5, 10, 15, 20, 25, so on and so forth. Skip counting by 5s is equivalent to multiples of 5. Multiplication by 9, we are going to learn mental math strategies for that as well. And multiplication by 10 just corresponds to a place value shift. So for example, if we multiply by 0, 1, 2, 5, 9, or 10, all of these numbers should either be automatic from our properties, or we can establish kind of easy mental math strategies that can help us with multiples of, and specifically 5 and 9. We can use place value to multiply by 10. For example, 3 times 10, we can think of that as 3 tens, which is the same as a 3 in the tens place, or 30. So these multiples are going to reduce that number from 66, again I should have this memorized, I apologize, but all the way down to 15. So it's kind of misleading to think of we have to memorize our multiplication facts. Not really. It doesn't correspond to memorization of 121 facts. Really, the best way to handle multiplication facts is to use arithmetic properties, commutative property, identity property for multiplication by 1, place value issues for multiplying by 10, mental math strategies for multiplying by 9 that will involve the distributive property, previous facts from addition for multiplying by 2, if we use all of those thinking strategies to our disposal, we have taken 121 facts and reduced them to 15. Okay, so thinking about it this way, the way we approach the problem can make a very big difference in how our students learn these very important facts. And again, I'll attach a PowerPoint to this slide that will go into this in a little more detail.